This is the third video on electrolysis, and the first thing that we'll discuss is the NERNST equation, which is also used to determine the effect of concentration on the value of SEP. So let's take the example of the given equation, that is iron 3 plus electron producing iron 2 plus. Now for example, if I, let's say, increase the concentration of iron 3 plus ions. Okay, so firstly the E naught value for this is Fe3 plus 2, like this is plus 0.77. Now if I increase the concentration of Fe3 plus ions, whereas Fe2 plus stays the same, that's first they were both 1 mole per dm cube, 1 mole per dm cube. Now this is, let's say, 1.5 mole per dm cube. Then the forward reaction will be favored, right? So because the forward reaction, because equilibrium shifts towards the right hand side, the forward reaction is favored, so the value of the electrode potential will increase, right? So it won't be SEP anymore, it won't be the standard electrode potential, it will be electrode potential. It will be more than the standard value because the forward reaction is favored. However, if let's say we decrease the concentration of this, we decrease it to 0.5 mole per dm cube, then equilibrium shifts towards the left hand side, the backward reaction is favored, so reduction becomes more difficult and the value of E is less than the value of E naught. I hope that makes sense. What is the NERNST equation? So the NERNST equation is basically this equation: E equals E naught minus RT upon NF ln Q. Over here E is electrode potential, E naught is standard electrode potential, R is the universal gas constant, that is 8.31, temperature is always 298 Kelvin, N is the number of electrons that were used in the electrolysis, and F is Faraday's constant, which we did in the first video on electrolysis, that is 96,500. Q is basically the same as Kc, it is the ratio of the concentration of products upon the concentration of reactants. Okay, so now let's simplify this formula. So E equals to E naught, R we know is 8.31, temperature is 298 Kelvin, and we don't know, F is 96,500, and then to convert ln to Lg, what we do is we multiply it with 2.303 and this becomes Lg Q. So if you simplify it, this becomes E equals to E naught minus 0.0591 upon N times Lg Q. For those who don't have maths, Ln is basically logarithm with base E, that is exponent. Lg is logarithm with base 10. So this is the simplified expression for the NERNST equation, which we'll usually be using. Now one question arises in math students, that why did we replace ln q with 2.303 Lg_Q? So I'll explain that. So let's say we basically had ln q, and let's say it's equal to a value, let's say it's equal to q. So I can write q as e to the power of x. Now if I apply log on both sides, this will be Lgq equals to x Lge, so x equals to 1 upon Lge times Lgq. 1 upon Lge is equals to 2.303. So that is how we got that result. This is the NERNST equation of how to apply it. So the main things that we have to find is the value of n and the value of q. So first we look at the value of n. So if we have a half equation, let's say like Zn2 plus 2 electrons producing Zn, then it's pretty simple, n is equals to 2. But when we have a full equation, for example, we have chlorine plus Fe plus 2 Fe2 plus produces 2 Fe3 plus 2 chloride ions. Then we have to see the two half equations and write it in the half equation form. So this is basically, you can judge it directly as well, but this is the best method to ensure that you're doing it correctly. So chlorine plus 2 electrons, we know, converts it to 2 chloride ions, whereas for iron it's Fe2 plus converting to 2 Fe3 plus 2 electrons. So here you can see that 2 electrons were being transferred from iron 2 plus to chlorine, so that's why N will be equals to 2. You could even directly see that chloride ions are gaining 2 electrons, so that's why N will be 2. This is the safer option. Now the second thing is the value of Q. Q is equals to the concentration of the product upon the concentration of the reactant. These are the points to note, that concentration for all solids are constant, concentration for all gases are constant, so we don't mention these in the calculation for Q, and the number of moles are in the power. So let's take an example. If we have let's say magnesium solid plus copper 2 plus aqueous converting to magnesium 2 plus aqueous plus copper solid. So the value of Q will be concentration of products. Over here we'll only take magnesium 2 plus because copper is solid, and then in reactants we'll only take copper 2 plus because magnesium is solid. So this will be the value of Q. Let's take another example. So if there is chlorine gas plus 2 iron 2 plus ions aqueous converting to 2 chloride ions aqueous plus 2 iron 3 plus ions aqueous. So over here the value of Q will be chloride ions, the concentration of chloride ions, and squared because it's 2 moles, then concentration of Fe3 plus ions again squared upon, we won't take chlorine because it's gas, so it will be Fe2 plus again squared because it's 2 moles. This is how we determine Q and N. Very basic question. So over here we'll use the formula E equals E naught minus 0.0591 upon N LGQ. So E naught is given 0.34 minus 0.0591 upon N will be 2 over here, and then Lg, so it's product is a solid, so that will be 1 upon the reactant is copper 2 plus, which is aqueous. Its concentration is given as 0.1 molar, so 0.1. So we get E as plus 0.31 volts. So what does this answer tell? Since we're decreasing the concentration of copper ions, for SEP it's 1 mole per dm cube, over here we're taking 0.1 mole per dm cube, so the copper ions concentration is decreased, so that is why the backward reaction is favored and reduction becomes more difficult, so the value of E is less positive. This is the second equation. Now again we need to find E, so that is, we need to find E cell, so we'll use E naught cell minus 0.0591 upon N LGQ. We need to find N and Q. So first what I'll do is I'll write the half equations of magnesium and zinc. So basically let's look at the data booklet. So for magnesium the equation is this one, minus 2.38. It's Mg2 plus 2 electrons. Using magnesium, E naught value is minus 2.38. For zinc, it's Zn2 plus 2 electrons, and it's negative 0.76. Zn E naught is negative 0.76. Okay, so we'll be flipping the magnesium equation because it has a more negative SEP value, right? So the value of n will be 2 because there are 2 electrons, they'll get cancelled out. Then for E naught cell, the formula is E naught right minus E naught left. This is E naught right because it's less negative. This is E naught left. So minus 0.76 minus 2.38. It's E naught right minus E naught left. This is coming as plus 1.62 volts. Okay. So E cell is equals to 1.62 minus 0.0591 upon NS2 Lg products upon reactants. Products में zinc is solid, magnesium 2 plus is aqueous. We will ignore zinc. Magnesium 2 plus is 0.01 molar. 0.01. In reactants, magnesium is solid, we'll ignore that, and Zn2 plus is 0.1 molar. 0.1. You solve this, you'll get the answer plus 1.65 volts. Thing concept is Gibbs free energy change and the relationship between Gibbs free energy change and standard cell potential. So for that we have this equation, delta G naught is equal to negative N F E naught cell. Negative G naught is Gibbs free energy change, E naught cell is standard cell potential. Negative N is basically the number of moles of electrons. It's the same as the N that we had in the NERNST equation. And F is Faraday's constant, that is again 96,500. It's very simple. The question is straightforward. This is one example. Calculate the value of delta G naught for this equation. So we need, this is the formula. Right, we need N, so we need to find N. What will N be? We can see that magnesium is losing 2 electrons, silver is gaining 2 electrons, so that means that N will be 2. You could also do this by making the writing the half equation and seeing the number of electrons, balancing them, and through that process, this is the shortcut. Then F we know is 96,500, and E naught cell we'll have to find. So for E naught cell, I'll get the data booklet. So it's magnesium and silver. The value for magnesium, it's visible, is minus 2.38, and for silver it's plus 0.8. So this will be E naught right, this will be E naught left. So it's 0.80 minus 2.38. So 0.8 plus 2.38, that is 3.18 volts. So delta G naught will be equals to negative 2 96,500 3.18. So delta G naught is equals to negative 613,740 in joules, and it's negative 613.7 kilojoules approximately. This is electrochemical series, which is a continuation of an O-level concept. So electrochemical series was done in O-levels. For first we'll do the cations one, but we'll understand this more using electrode potential values. So this is the electrochemical series. What this tells us that this is in order of decreasing reactivity. So potassium is more reactive than silver. So potassium has a greater tendency of remaining as an ion because it is more reactive, whereas silver has a higher tendency of forming a metal again. That is because the SEP value of silver ion is higher, and it is easier to reduce it to silver metal, whereas for potassium it's difficult to reduce it. Potassium ion, it's difficult to reduce it. So that's why in electrolysis or in cells, silver discharges first at the cathode. That is because silver has more reducing power. Silver ion has more reducing power. It is a stronger oxidizing agent. So this discharges first from the electrolyte. Now let's say, for example, if we had, so basically the ion that is lower down the reactivity series discharges first. So let's say if we had a solution of, let's say, NaCl plus H2O. So the positive ions would be sodium and hydrogen. Now hydrogen is lower down in the reactivity series. It has a higher SCP value compared to sodium. So that's why hydrogen will discharge first, sodium will discharge after that. This is for cation. Anions, there is a different method that's used to determine which ion will discharge first. So from O levels you'll remember that oxo ions, that is sulfate, nitrate, carbonate and phosphate, do not oxidize or do not discharge at the anode, right? After that there's the halides, fluoride, bromide, iodide, and then there's hydroxide. So usually there's either hydroxide with one of the oxo ions, in that case hydroxide discharges, or there's hydroxide with one halide, in that case the halide ion discharges. The reason for that is, let's see the equation for chloride. So the equation for the oxidation of chloride would be 2Cl negative going to Cl2 plus 2 electrons. So 2Cl negative going to Cl2 plus 2 electrons. So then the E naught value would be, for the forward reaction it's plus 1.36, for the backward reaction it will be negative 1.36. For hydroxide, the equation is, this is the forward equation, but we need the backward equation. So it's 4OH negative, reversible sign, O2 plus 2 water plus 4 electrons. E naught is equals to negative 0.4 now, because it's the opposite reaction. Now you can see that this is more negative, so it's easier to oxidize. That's why chloride will discharge first. This is how we can determine that halide ions discharge before hydroxide ions discharge before oxo ions, right? Now for example, if we had, let's say, MgCl2 plus water, so the anions would be chloride and hydroxide. So over here chloride would discharge first. Then if we had, for example, let's say maybe magnesium sulfate and water, the anions are sulfate ion and hydroxide ion, so hydroxide will discharge first. That's all from electrolysis. I hope you understood things from my lectures. Thank you.